on percolation, on books by Professor Havlin. And then 25 years later, when you see that he's still ahead of you, and you still learn about the new things he's still doing, you recognize that you are in front of someone special. And this is because I think it's a real pleasure to have with us, to have him. So thank you for coming, and the floor is yours. And sorry for the delay with the computers.
Thank you very much, Emilio. Thank you, all of you, for coming. I hope after my talk you will learn something from me. And what is the title, as you see, I will ask to speak a little bit about new directions and application in network science. Network science became very active in the last 12 years. And I will tell you also the reasons why it became active. And I will show you one new direction, which is going from single network to interacting networks. Here you see a single network. The single network can represent like electric grid, communication system, transportation. A network means that you have nodes and links or services, but in many cases, in most cases, actually networks are not isolated, but they interact with each other. And the interaction that I speak about is actually there are two types of links here. If you look here, you see black links and red links. The black links are the classical links that we use in statistical physics. These are the links that when we say calculation, we want that the majority of nodes will be in contact using these links. So these are called connectivity links. But introduced here in the last 2 years, we started to introduce new type of link, which actually exist in real system, and this I call dependency links. I put it in red. Dependency links mean that a node in one system depends on another node in another system. If this fails, this also fails. So there are dependencies between the system, and this is the new phenomenon that I will try to describe today. And this may lead to cascading failure, because you can see here, for example, this node fails, and then other nodes in other system fail, and other nodes in this system that depend on this. So it will be cascading that can lead to catastrophic failures. So let me start, because I was told that not all of you know what is network. I will start with introduction to network and why network became so active in the last 10, 12 years. So let me first start with introduction. Since 2000, about 2000, we have a huge, extensive studies on networks, and always usually was single networks. This is a network, for example. This is a network where we did for communication. It's a cell phone network that people can speak with each other. The brown are the new new operating system. So the brown nodes, and the blue are the nodes which are the regular system. And you can see you have only small clusters of new. And this was in 2009, and this was the reason why epidemic should not spread through the smartphones. Smartphone can only speak with few smartphones, but not all of them. Why epidemics? I mean epidemic viruses in the smartphone system. But what is a network? Network consists of n nodes and m edges, or 2m links. And in mathematics, the word for network is graph. In mathematics, we call it for many years graph, a graph theory. Now, complex systems, why networks are important? Because we can describe many complex systems by networks. For example, the internet, we can say nodes represent computers, and the links, the connecting cables between them. When we send a message by email from one place to another place, it goes through the computers, through the links, through the internet, and it comes to the destination. So this is a network of internet, social network. Social means nodes may represent people, and the links, the relations. And not everyone is a friend to everyone, but those that have friendship, those are their links. Climate system, and this is what I will speak a little more here. There's an expert, Jovan here, did a lot on climate system. And the nodes represent location, and the links represent similar climate in both locations. This is a new paradigm in climate, that not only testing the climate in one place, testing in another place, this teaches us something, but the interaction between places can teach us something new. Because maybe that there are interactions which are not seen just by looking in one place or in another place. These interactions you can imagine like you have two random oscillator, yeah, oscillators. But on everyone it's chaotic, everyone you measure chaotic, but if they are coupled, they show that there is a link between them, and these links may teach us. And the dynamic of these links may teach us in climate also. And this, I will speak a little bit about this also. Now, because of the network theory that we learned about network, we had also many successful research. For example, we know how to make efficient immunization strategies, to identify key players in the network, what are the most important nodes in the network. Robustness of network is one which I will speak a lot in this talk. Climate network, physiology, I will show you also physiological network, protein network, function, we can learn from the network about the function. And this was a great success by Bar-Ilan, who looked on the network and the structures inside the network, and he could identify what are the functional properties of this protein that were not known before. So network is a very important field that can be very useful. And the network, I can show you how it is compared to other studies. These are citations of networks. I compare it to other, like Chaos, Wilson, you know, the randomization group, and Feigenbaum, the three fields. You see, they were started around 1975, 80, and these are the citations, how it goes from 0 to a number about 200. Now when we go to other fields, all the fields are in statistical physics, fractals, neural network. We look on the main papers, and we see also that around 200 was the citation after it started in the years of 80, or by Mandelbrot, you know. But now what happened to network? If we look on networks, we see that really blow up. I mean, the network is become very active and very important, and this is only until 2008, and I think 2012 it is already here, or somewhere outside the screen. So, why network is so important, and this is what I want to tell you. So first of all, we are in an institute which belongs also, which is part of physics, so I want to emphasize that networks in physics were very relevant. And the network that we use in physics were very simple network, relatively, like a lattice, two-dimensional, three-dimensional, hexagonal, and also random networks like this for the structure, and many phenomena in physics depend on the structure of the system. Phase transition, for example, and others. So networks is not unfamiliar to physicists, but the networks that we have in the real world today are much more complex than these systems. And let me summarize with the classical view in mathematics. So I showed you in physics, we studied lattices, but in mathematics they used to study a Poisson network. Poissonian network by Erdo Sheni. Poissonian network means that the degree of a node is the number of links per node, is distributed as a Poisson. You remember, in physics we usually have a delta function for the degree. Every node has the same number of links. For example, this node has 4 links. You see, everyone has the same. But in mathematics they were a little more relaxed, and they say, let's assume that we have a Poisson distribution. This is the Poisson distribution. This is similar to what we see in roads, or in America, for example. But we realized only in 2000, or 1999, just 10, 12 years ago, 30 years ago, that the real networks are not Poissonian. Most of the mathematics, or people in computer science, they assume that networks are Poissonian. This was the assumption when they studied computer networks, or internet. But when we realized, only in 1999, it was realized that actually networks are more complex. They are not Poissonian, but they have a broad degree distribution, like this, which means, you see here it decays very fast, Poissonian decays very fast, so the chance to have a high degree is very, very small, negligible. But in power law, this is a power law in the log scale, power law, the high degree can have a good chance to have. And this is like not like the roads, more like the airline, which started 100 years ago, airline networks, and you can see some places have very few links, but some places have very many links. And this was found also, the scale-free network, power law, which is we call scale-free, can characterize also the airline network, but not only the airline network, also many other networks. For example, the internet, and this was a paper by 3 brothers, Faluzos. Same name, but they're brothers. But it's a famous paper, very well cited. And they realized in 1999, surprisingly, they say, We couldn't find Poisson. The Poisson was so deeply inside the mathematics, and they say, we cannot find Poisson. This is something which is not Poissonian, which is like a power law. So, and this is the internet, how it looks. So the internet looks really very complex. You see, this is how it looks all over the world. Of course, it's part of it. We have many more cables here, and this is how it looks. So it's a power law, it's a broad. You have also hubs of 10 to the 3. You see, in computers that have many links, and not only few links like in the Poissonian. And when at the same time, almost, Barabashi looked on the WWW network, and he realized also the same phenomena. Look how complex. It's not a lattice, or not a random network that we saw before, a Erdős-Rényi network, Poisson. But you have nodes which have few degrees, and you nodes that have many degrees, and all kind of nodes here. It's a broad distribution. And this changed the way that people look on network, because it's a new symmetry. I mean, before it was more symmetrical. In physics, if you have a symmetry, you have laws. But if the symmetry breaks, then you have new laws, and the laws are different. And this is what makes very interesting people to go and find what are the new laws caused by this change of symmetry. Also in metabolic, you see also the broad distribution. So it means, and this was in the early year 2000, and it goes on and on. Now let me tell you, for example, what is the difference between the classical, exponential, Poissonian, this is the Poisson degree distribution, K is the number of links per node, and you see here you have maximum 4 or 5, but not more. Or this one is escape-free, where you have a power law distribution, you can have nodes which have many links. So this is exponential, this escape-free, and I want to compare between them. So first of all, let me tell you that while here, the distance between nodes, distance is how many jumps. For example, if I send an email here, and I want it to reach anyone here, and I want the average distance, the average number of steps that it goes, it will be log n. Log n means a small number, which is, that's why it's called small world. You remember the name small world appears in many cases. Small world means that if I have a population of 10 to the 6, I have d is the distance between the people is about 6 steps, and this is called 6 degrees of separation. There was movies and shows about this, how people are close to each other. If I want to find a connection to Obama, for example, I think I need 2 or 3 people to reach him. So everyone, it's not only, I mean, you find a person that knows me. So this is the small world. However, what happens in this one, when you have a scale-free distribution, the distance even becomes lower. Instead of log n, it becomes log n. Log n is much smaller. And this is called ultra small world. So social networks are scale-free, because you know, some people have many friends, and some people have less, and people found a broad degree, so it's log n. So the distance here is ultra small, very small. And so this is one result. The other result is about the stability of the network. Stability of the network, how many nodes you have to remove here, and the rest cannot communicate. So in the classical system, I call it the classical Erdős-Rényi, which is 1960, was actually solved by they suggested this model, and they solved all the mathematics regarding almost all. Later came Bolobash, was a student of Erdős, he solved many other properties, and they found that the number that nodes that you have to remove, if you keep 1 over k average is the average degree, if you keep 1 over k average, still the network collapses. If you remove 1 minus 1 over k average, still the network. But if you remove more links, then more nodes, then the network collapses into pieces. This is how you can describe it in a mathematical graph. It means here the system is connected. This P infinite means what is the fraction of nodes that still can communicate. Communicate is here. We call it also the giant component. So when all nodes, like this case, when all nodes are intact, all network can communicate, so it's 1. But when you start to remove from here, you remove, then the giant component or the network which can communicate becomes smaller than 1. And then there is a critical threshold below which if I remove more, the network collapses into pieces. This is like a critical phenomena, not like, it's a critical phenomena that we have in physics. I mean, when gas goes to liquid and liquid goes to solid, we have such critical phenomena of critical exponent. So in a critical stage at which the network collapses. While when we go, this is in the ER case. When we go to the scale free, in this case, it was found that PC actually goes to 0. It means ER, scale 3, is much more robust than the Erdős-Rényi. It means you have to remove almost all nodes in order to collapse the system. And the reason is because the large degree node, which we call the hubs, they actually hold the system. There are very few, so to reach them randomly is very low probability. You don't reach them if you remove randomly. Of course, if you attack the hubs, you can destroy the system very easy. But if you remove randomly, you don't reach the high degree. And then the system, the PC, can be proven to be mathematically to be 0, means that it's very robust. So this was started to see new phenomena that did not exist in Erdős-Rényi. I mean the log-log-n and PC0. And even more than that, Erdős-Rényi already in 1960 solved mathematically, analytically, and this is important, that's why I give it here, in exactly how P infinite, how this function behaves as a function of P. So this is the form that you see here. If you, as a function of K, as a function of P, if you solve this equation, you get exactly the curve how the network collapses when you remove 1 minus P nodes from the network. So this was exciting in the early 2000s, and people become more. I show only a few results, but some of them, but many more results, show that actually we have a new class, new universality class, which has new properties.
The laser pointer is going down.
Going down. Oh, thank you. I didn't notice. So, but can I use also the other side? Okay. The laser. I hope this is better. But I think my laser is okay. Let me try mine. Something happened. I don't know. Can you check? You don't have somebody. Yeah, mine is better. Let me try to continue. I hope it will work. Oh, what to do now? Oh, 1 minute. Oh, I see, because it took away or something. Yeah. Okay, so now I will use this, but I cannot. You think I can move the slides now? Yeah, I can move. Okay, so this was the situation, and it brought also to many applications, which I will show you. Some applications. This is better, no? No, now I need the. Will it work? Yeah, it works. Thank you. So, and now comes several applications. For example, this was a project similar to the link, which we call EpiWalk, and this was related to epidemics, where we can, using a network, we can predict how epidemics will spread, and we can compare it to real spreading. And you see how similar it was spreading in Italy. And this is not my work, it's a work by Vespignani, and not only in Italy, he did it in many countries, and could predict how spreading occurs only with knowing the information about the transportation networks, because the disease mostly using, I mean, the people which are infected, they use transportation, they bring the disease from one place to another. So if you know the network of transportation and the weight of the links also, how many people go from one place to another, transportation means train, means also flights, he included them, and then we can predict about the epidemic spreading. And also, as I told you, from the network, one can predict the function of the protein functions, and this was done also successfully. I will show you only some slides that show successful project. Now, this is a work that was done in my group by Avi mostly, who is here, and this was related to climate network. I told you many things were done by the group of Jorgen Kurz, who is here, but this was done already in 2008, where we find that if you describe the climate as a network, meaning that the nodes are here and the links are the similarity between different places, and now you calculate the total weight of the links, how similar it is the weight, and you can see that during El Nino, the weight of the link becomes very small, very low. You see, these are the El Nino periods, you can see it here. This is the temperature measurements that you have here. During El Nino, this is from year 1960 to 2005, I think, yes. And you see that the network follows the El Nino regime. Also in places that you cannot see clear the El Nino, like here, you don't see. These are different networks, you see all over the world. Here you don't see the El Nino clear in the temperature, but you see it very clear in the network. So network is very sensitive, for example, to climate changes. And not only on the globe, these four pictures are the same network, but at 5,000 meters above the sea level. And we see also the El Nino. So El Nino, the network is very sensitive, the interaction between places is very sensitive to El Nino, and we can maybe use it for prediction of El Nino. We have now a paper that we submitted, because this phenomenon occurs slightly before El Nino, and maybe we can predict better the El Nino, when it will occur and how strong it is. And not only this, in a recent paper which was published in Physiological Networks by Avi, was showing that actually the El Nino basin, which is in the Pacific, becomes autonomous during El Nino effect. When El Nino occurs, it becomes autonomous. It means it only can affect other places of the world, but it is not affected by the other links, because links can be infect somebody and can affect also outside. So it was useful for studying this, and many more results by the group of John Cookurt and by our group also are showing that network is very useful to study climate. Now another field, for example, in a work that was done that's showing that connections are not everything. Usually people think that a person that has more connections is more influence, but this is not true. We show in this paper that connections are not enough. You need to be more in the center of the network. And what is the center? That not only that you have many connections, but your friends must have also many connections. Because otherwise, if you have many connections and your friends are only connected to you, they cannot spread everything, you see. So you need more. And this is done by a method which we call Keiko, and this was interesting. Another work was done in physiology network. I'm showing you how in different fields can this network study help. And this shows here, what you see here, is that during sleep, deep sleep and light sleep, which is usually regarded by physicians like similar, very similar. And they every name, different name, but for different reasons. What we see here that there is a very different behavior in the network which connects brain to heart rate, to respiratory, to chin, to leg, to eye movement. All these movements are related to this. And if we do the interaction between these systems, we can make a network like this. And what you see here, that this is during 4 minutes. This is 4 minutes. So during these 2 minutes, before going to light sleep is a stage in sleep. Deep sleep is a very deep sleep. The network is almost disconnected. There is only links inside the brain. However, when you go to light sleep, all interactions appear. All the systems appear. It means that the deep sleep is actually the brain is become isolated. It sleeps very well. That's why maybe. And then only later, when you go to light sleep and also REM and also wake, they are more connected. So this was published in Nature Communication a few months ago. Also, you can, if you know network, you can improve against attacks. And this is a paper that appeared in PNAS that shows how to improve. You can change very few links and make the system much more robust against attacks of the network. So the network is useful also for this. So why do we need, if you know so much about network, why do we need a new direction? You can say that we know a lot. But the new direction comes, motivation, for example, as this appeared in the Boston Globe. You see cascading disaster in Japan. What happened? That the nuclear and the tsunami brought to the nuclear plants to break, and the electricity breaks, the transportation breaks, the services break. So everything, all the systems become not functional because of cascading between system and system. And we study usually networks, only one system. We didn't care about the other system. But the interaction between systems become more and more stronger during the technological evolution. We have more interaction between the systems. So the interactions were not taken into account. And this is what we try to do in the year 2010. when we started to have a series of paper. Started with this paper and then several more, but there are many more now, where we said, okay, why to look only on single system? This one, this one, this one. This one can be, for example, this is electric grids, the other is communication and transportation and services. There can be more systems, but what happens if you have dependency between the systems? One system cannot function if the other cannot give them supply. For example, if you have communication system, if there is no electricity, how communication will work? There is no communication. Or transportation needs also. So there are interactions between the systems, how to take them into account. And this was, so what I want to tell you, why the motivation was that recently, 2 years ago, 3 years ago, most studies focused on single network, which is isolated like this, and is not influenced by other systems. But this is rarely occur in nature, not in technology, and this is also analogous in physics. 70 years ago, not in my age also, people studied isolated atoms, isolated molecules. I mean, it was no interaction between molecules and non-interacting particles. And then, but of course, this is, people learned later that physics comes from interaction between particles. And then you have a much richer phenomena. You can have condensed matter, you can have different states like liquid, gas, and like liquid and solid. And the interaction becomes very important. And this is very similar. If you take interacting networks, you see also results which are very different what we know from single network. And this becomes a very rich field, I hope, and people start to work on interacting networks. Not only because it appears in nature, because it's very relevant and very different from single, like, you know, like an interaction between molecules and spins. You cannot get a magnet without interactions. You can get materials without interactions. Now the interaction is not new. That's what I want to show you. Already 11 years ago, engineers knew that there is dependency, and look how they call this. They call how interdependent are infrastructure. Infrastructure depends on each other. And you can see here, power grid depends on natural gas, transportation on oil, on water, on telecom, and telecom depends on all other. So the interaction was known. What was missing is a systematic way to study this. How to study in a systematic mathematical framework to understand better what happens. And this is what I will try to show you. But before this, let me demonstrate you a real event that resulted from interacting between systems. And this was the Blackout in Italy in September 28, 2003. And this was documented by Rosato in a paper in 2000. He studied, he's an engineer, and he studied what happened in this blackout. And he realized that the blackout occurred because you had mostly because the interaction between, these are the power grid, and this is the communication system. You know, power grid cannot work without communication system. We need to know how to transfer the electricity from place to place. So he realized that the problem was the communication between the two systems, and the cascade of failure, there was a failure here, and since the nodes here in the communication depends on the electricity, some other nodes fail, and I will show you how it goes. And this leads also to other networks which are related. The railway network, healthcare system, financial, everything stopped this day to work. Italy was in a blackout. So, and also other blackouts in America and other places documented, and they show that cascading failure between systems are very important. And let me show you the example that in Italy what happened. So there was a power grid here, a power station here, and this power station did not supply power to communication systems here. But this was not only the damage. The damage was that other communication in green, they belong to the network here only through these stations. It means that this station doesn't work, they are like not working because they don't have any information, they cannot get information, because they were connected in the communication only through these places. You see, this one was connected to this one. So they fail also, and they cause cascading failure also in the other. You see, this one failed, and this one failed, and this one failed. And now further damage goes to the network, to communication, and suddenly the power grid was split into two, and then they stopped all the power in Italy. So you can imagine that infrastructures, but not only infrastructures, but many aspects, many other different aspects of life, nature, technology, they have the similar interaction between systems. Physiology, I already showed you. The human body can be seen as interdependent network. The cardiovascular system, the respiratory system, the brain network, and the nervous system, they all depend on each other. Each one is a network, but they depend on each other to function. Also in economy, also in transportation. So, and the question is, what happens when you have systems that depend on each other? As you can see here, for example, two networks here. If I have failure here, it causes failure here, and the failure can come back here and can go back here. This is when you have two, but when you have three, it's more complex, and four is more complex. So you can have many networks. And the question is, can we make percolation like we did for single network also to study interacting network, interdependent networks? And this initial work was done in these two papers, one in Nature and one in PRA. And then when we go to this, so let me compare. I will not go into detail, just compare what is the difference between single and coupled networks. So you remember these two single networks, as I showed you before, but let me discuss mostly the ER network. And the ER network, when you couple it to another ER network, what happens? Instead of having a transition like this, as I told you, this is the formula that was derived already 52 years ago by Erdoshani, how the giant component, if you remove nodes from here, the giant component becomes smaller and smaller and smaller till it breaks down. This is continuous. The surprising result when you take two networks that depend on each other, instead of continuous transition, when you start to remove nodes here, they have failures also here, and these failures bring here, and you have cascading between the two. So if you remove little nodes, few nodes, it doesn't make a big damage. More, it doesn't make. But when you get a critical point, it makes such a big damage that it drops abruptly to zero. And this is very important because abrupt transition is very risky because you don't know here, okay, if I am in single network, I know some more damage to the system will lead to small damage to the network. You see, I come here, from here to here, I have the network is a little smaller. I think it's again, maybe I push too hard, no, so much, okay, maybe okay, but in this case, if it's coupled, if the two networks are coupled, I can be here, and 80% of the people are functioning, they can communicate, the network works, but very small damage, further damage, will lead to collapse of the system. So we are in a great risk. So our society is much greater risk now because of the coupling between systems. And I call it a new paradigm, abrupt transition due to cascading failure. Let me show you how the cascading failure looks. How they look during this process. This process I come here, and I remove this part. You see, this part I removed. And then the network is here, but it doesn't stop here. It continues to go down, 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 but not with my removal, only because of the cascading between the system. I don't remove anymore. And you see, this is the natural cascading that occurs in the system, and the giant component goes from being here to being being zero. It means it becomes collapsed. By this shape, this is a nice shape. It goes first, it jumps dramatically, and then there is a slow, and then it goes. If you look on this figure, I'm sorry, if you look at this figure, in the beginning it goes fast, and then it goes very slow, and then it goes again fast. I mean, the dramatic, very dramatically it collapses. So if we learn this, we understand this, we can maybe learn how to avoid this, or at least if we are in this stage, we see it's very slow, maybe we can change something in the network and try to avoid, instead of falling down, it will be stable here, you see, during time and will not fall down. What is surprising that we can also solve analytically, and if in ER, PC, you remember this PC in ER was 1 over K average, this number. In two networks, PC is 245% more than PC, I mean much higher PC, the amount that you need in order to, the network will survive. Not only this, if the coupling is strong, you have a sharp transition. Coupling strong, let me say, what is coupling strong means that all nodes here depend on all nodes here. This is the strongest coupling. Every node in one system depends on another, but if you weaken it, you take only a fraction of nodes here that depends on a fraction of nodes here, which we call it Q. So if Q is smaller, And here you take an example of Q 0.8, 80% here, depends on the year, and 80% here, you have a sharp transition. But if Q is 0.1, you have a smooth transition, like 0. I mean, if you have no coupling, little coupling, the system does not fall dramatically. But we have also a new phenomenon which is like physics. And let me show you. In physics we know that you have a liquid gas transition, depends on pressure and temperature, and this is the first order. First order means a jump, abrupt change from liquid to gas if you are in this stage. But when you reach this point, it starts to be, the critical point, it becomes a smooth transition. Smooth means that it goes from liquid to gas very smoothly. It becomes liquid, less and less liquid, till it becomes gas. The same phenomena, the same critical point appears also when you have interaction. Not only interaction between particles here, interaction between networks. You have also a sharp transition here. This is the first order transition. If you have a strong dependence, this is 1 minus Q. Strong dependence in this regime, you have a sharp transition. This is a first order transition, first order. But when you go to this place, you have a smooth transition, which we call a second order transition. So similar phenomena that you see between interacting particles, we see also when you have interacting networks. So let me, I think I will soon finish, but let me just show you what you can do mathematically. You remember I told you about this result. I want to go back, this result. This was 60 years ago for a single network. The question we ask ourselves, what happens if you have not one network, you have 2 networks, 3 networks, and we solve it analytically, and we find that this has a power, n. N may depend, is actually the number of networks. And when Erdős solved, he solved it for 1 network, so he got n equal 1, but he didn't try it. He didn't try it to the power 1 here, but if you study not 1, you study n network, like here 5 network, or any number of networks, but this is a tree-like network, like this, it means that there is no loops in this system. When you then it depends on the number of networks, and you get the generalization of the formula. You see, instead of getting n equal 1, you get here n. You have to put here n is the number of networks. If n is 1, this is the classical result. And 1 is smooth transition. You solve this for n equal 1, you get p infinite goes to 0, very smooth. But when n is 2 already, you see the jump. When n is 3, you see the jump. So you can generalize now, not only single network, but you have n networks. And this was done in this paper, but not only one generalization. This is one type of generalization, but you can ask yourself what happens if you have loops. Loops you can have, and we study, for example, a system like this. Each node is a network, a random network, but the random network depends on m other network. For example, here m is equal c. So you have a network of network. Each network depends on the same number of networks in the network. So this one you see depends also on c. Each one depends on c in this case. But you can have a general formula for k average is the degree inside this network. M is the degree of the dependency between the networks. And the Q is how many nodes here depends on here and how many nodes here depends on here. So you have 3 parameters. P is how many exist in this network, how many, 1 minus P, the amount that you remove. And then you have the formula, a general formula for P infinite, where you have here Q, M, and K, and P. And if you substitute now, for example, M equals 0 in this formula, this is for the Jacob, you get exactly this result, the single network. When M is equal to 0 means every network does not depend on other networks, just isolated. M0 means no dependency. When you substitute M0, you see exactly what happens is what is left is this one. So it means you get this. But not only when M equals 0, if you take Q equals 0, Q equals 0 also, no dependency. Q tells you how many nodes in one network depend in the other network. You get also the same formula. So for M equals 0 or Q equals 0, you get the same. And you can also generalize it QC and PC to find QC means the transition from first, second. For Q, dependency below QC, you get a smooth transition. For Q above QC, the dependency is strong, you get a jump, abrupt transition. So you can see that, and this was in the paper of Nature Physics. So you can see that we go from single network, as I showed you, to many networks. We get generalization of network, which include the result of a single network also. So So let me summarize, because I think it's already time over, maybe, yeah. And so let me just summarize and leave you for questions. So I think I presented here a statistical physics, first statistical physics approach for robustness of network, of interdependent network, where we see cascading failure. And I told you it's a new paradigm. Why new paradigm? Before we saw that the system collapsed like this. This was our intuition all the time, because we studied only single network. But when we study coupled network, interacting network, we learned that they can fall also from year to year, dramatically. It means small damage, or even one node can make cascade in such a way that the system will collapse completely. So new paradigm, abrupt collapse compared to continuous in single network. And the generalization of new network shows that 50 years of graph theory and percolation theory is only limited case in n equal 1. But larger n become more vulnerable, and you can make generalization to larger n to see new phenomena which we see here. So I think I will stop here, but just to tell you that the program is very rich. I didn't tell you, for example, all the talk was on random network, but what happens if you have features in the network, like clustering, if you have a correlation of the network, or if the networks are embedded in space. I didn't speak about network. The results are also very different and very rich. So if you take two networks which are embedded in space, like electricity grid and another network, transportation maybe, you can expect even more vulnerable than this. And this is a paper that maybe another, this paper, where it shows some preliminary, results that show that much more vulnerable when you have a space restriction, because the space makes everything more vulnerable. Even a single network, let me tell you. If you take a random graph with k is equal 4, PC is 1 over k, k average 4, PC is 1 over k, means 1 over 4, it means you can remove 75% of the node and the network still exists. 1 over k average is 1, 4. If you take a lattice where k is 4, PC is not 1 over 4, but almost 0.6. 0.593. It means if you remove only 40% in the lattice, it collapses. So single lattice is more vulnerable than the random, because in random you have long range, like you have long range connections, while in lattice you only connect to your friends in the space. So you don't have these links which hold the network. So imagine now when you take interacting network, they become even much more vulnerable. So vulnerability becomes even stronger when you have a space restriction, spatial embedded network. But this I don't have time to speak about now. So thank you very much.
Okay, thank you very much for your nice talk. And okay, questions or comments on the talk? I start with something that, why is this, I mean, you have shown at the beginning a plot in which it seems that the network studies are different from other, so it seems it's not simply a fashion, or at least it's not a fashion as before. I mean, why is so many people, new scientists, interested in networks much more than in other
I didn't say this, but networks is relevant to many disciplines. For example, in computer science, they are very interested in networks. Physicists are interested because of physics. Also, social scientists. Many social scientists are interested in networks because what is a social system is interaction between people, and they are interested. So there are many social scientists that also go to network. Of course, mathematicians are also interested, and also engineering. Engineering, I mean, they understand now that if you know they call it reliability of a component, it does not tell you about reliability of the system. They have institutes about reliability everywhere in the world. Reliability, how reliable is the system? But they don't include the network reliability. It means I know reliability, let's say this component can rely, I can rely for 5 years, for example. It's lifetime 5 years. But if you have different, if you have a network of systems, you want the reliability of the network, this is very important for them. And they start now to realize that network is very important, and they have many conferences. So in many directions, they realize the importance of network, and they jump into this, they realize that. Also, I want to tell you that before, when people use graph theory, Hertzsprung graph, they came to some wrong conclusion, and this was frustrating for many people. They could not understand, for example, why viruses in the internet are so much alive. According to the Hertzsprung theory, if you buy so and so many antiviruses, it should already die. I mean, all the viruses in the internet. But they existed. Only when we understood that PC is actually zero, that everyone is to buy almost antivirus in order to stop the viruses, then they realized, and it became more, I mean, people understood that the new field is important from almost every discipline, economics. You can see many papers where they realized that networks in economics are very important. So I think it's very interdisciplinary. That's why it is.
Questions, Ingo?
A very general question. How does nature cope with this vulnerability? If we think, for example, of physiology, nervous system, system like
okay,
that,
this is a good question.
To cope with it.
We have, what do you mean nature? Okay, so let me, as I told you, I think I showed an example where you can see in the climate network, you can see effect changing climate. And I think we are only in the beginning. I think John maybe can tell a little more. He has also done where he studied interacting between it. For example, you have different layers, different heights. Everyone is a network, but they interact between them. So they took into account this interaction between networks, between different layers. So you can, we don't know much, but my feeling is that the interaction in climate was not studied so carefully as it needed, and network can help a lot because actually the links in between places also have a dynamics, and this dynamics was completely neglected by people in climatology. They studied links, but they look links over a long time, but they didn't see that link can appear and disappear, for example. And this is, I think, advantage when you study network. You take a picture, snapshot of the climate network, and you take it another time, and you see how the network itself, the climate network changes with time, and then you can see some phenomena. Now, how to use it to improve, if at all, I don't have that answer. But it's only starting, I think. Yes.
More questions, Manfred?
But is it always so easy to distinguish between different networks, to say this is one network and this is the other, and they do not belong to each other? Because the climate example, you said, well, then this
which example?
The climate example.
Yeah, I agree.
Then you took the hate. But
I agree. So some networks you can distinguish very clearly. For example, transportation and electricity. Electricity goes in the electricity grid. But you need to include such phenomena like dependency between networks, which was not included before at all. I mean, in the theory, we did not have dependency. So dependency is very... Now, of course, you can study that you have both. You can use... If you can use two networks, for example, you have two transportation networks, then you have also dependency, because, for example, if the train cannot go to the airport will be almost empty, in some places at least. Yes. So the train and they depend, but also they help each other, because if I cannot go in the airplane, I can take also a train. So sometimes the network can help each other and can reduce the vulnerability. But what I showed here is the dependency if you have between networks, it only increases vulnerability, and the vulnerability becomes very very strong because of cascading failure, and this was documented in Blackout and other examples. Please.
It seems to me that's kind of paradox, because if you focus on simple network, and you will say it's quite robust, and if you look at the network of networks, it seems that you can cause cascading. And to me, this cascading is kind of artificial network of network, because it's kind of human beings network. And when you look at the ecosystems, and we cause a lot of problems to one network now, but it seems quite robust. So I think whether we didn't consider the complicated interaction between network of network, we just consider the linear interaction.
In some, that's related to this question, in some network you can clearly see that the one network is functioning different from the other network, and they depend on each other, in particular in infrastructures. This is clear. Now, in some places, we have to consider some dependency and also connectivity. In climate, there are both. You see, you can have two layers, for example, but sometimes something that happens in one layer can infect strongly the other layer also. But also it can also connect to one layer. For example, heat can go from one layer to another. So it's not as simple as I say. Not every time you can use the dependency. You have to be careful when you use the dependency. It's only when really you have dependency between the networks.
May I give an example? Spreading of diseases. In the old times, you had isolated societies. It was a small spreading, very limited. But these days, much more vulnerable.
This is an example of networks. How, when you combine networks, you can get more vulnerable. Yeah. In this case, for example. But in the simple case that I gave is because failure in one network causes failure in another network and comes back to the first one. You see? So it's cascading this kind of...
It is quite shocked to me that we have kind of probabilities that's similar to lattice, because we always consider lattice is quite linear interaction. And why our network of networks have this kind of probabilities of lattice?
No, not of lattice.
Because it have...
No. Okay.
More questions or comments? Please.
Yeah, got a question on the structure of matrix. It appears that, especially on scale-free networks, communities can appear. What is the difference between one single network with different interacting communities and several network, couple network? I mean, the mathematical framework is different, or?
Okay. In this case, that when I showed the links between the network are dependency. But in social networks, you can have also connectivity between the networks. But the mathematics is also known, and this was done, and let me show you. This is a work that started with Raisa de Souza. You see, Raisa de Souza, she considered communities which not depend on each other, which connect to each other. So she developed a framework. What I show here is more the dependency. It means that if a node fails here, it also fails there. Now, also in social network, there is dependency. For example, if somebody is in two networks, and if he fails to appear, he's sick, in one network, he will also fail in the other network. So there are also dependencies in social. You see, also in protein network, there are dependencies also. Why? Because some proteins, they function, different functions. So if they are dead, they cannot function, they don't function in several communities. So the dependency appears, but was not considered before. And this is the method to consider dependencies.
Okay, there were two more questions.
Two more.
I have one question regarding this network model relating to the climate. So
to what?
To the climate model. So if you have a power grid or something else, the network is more or less obvious. But in a continuous system like the climate.
No, when I showed the climate, I didn't claim network.
No, okay, but applying this theory to climate, are you not very susceptible to making interpretations which are just a matter of interpretation?
You mean this picture, yes?
For example, yes.
This
I mean,
picture.
what are the nodes? Do they move?
Here we assume the following: that the nodes are locations. This was network only. We take one network, another network here, another different four places in the world, and we assume a network. We separate it into four because we want to see if El Niño affects the network not only as global but also in different places. And we realize that in all places that you chose. Now, what is the network? Network are the nodes, and the links are the interaction, the correlation between the two places. How similar is the changes in temperature or in pressure also? This is, I think, this was done for temperature. No, but we show you only temperature, I think. But we have also pressure also. Another work is for pressure, and with the changes in pressure or temperature or the height. Sometimes they are very similar in some places, sometimes they are very different.
My question was more regarding to this cascading process. Because
I didn't mention. Here I showed only, I didn't show the cascading, I showed only the falling of the network.
So
It means the network was strong here, and during El Nino it becomes less. And we didn't understand this. Why? Because we know El Nino affects all the world. So we realized that the links that are failing are the links that go inside the El Nino basin. I'm sorry, I did some short. Oh, okay. Goes inside the. I don't know. I made the wrong answer. But maybe. Oh, so what I showed here, you see, links going in become very weak during El Nino events, and going out still exists. So maybe this is why the network becomes weak, because the El Nino becomes autonomous. This is what happened. Here I did not speak about networks. I said that there are works on network change.
Okay, there's time for one or more two questions.
Subsequent to that, if you call the El Nino phenomenon autonomous after a certain point in time, how can this be shown? I mean, in a highly complex and interdependent network of networks, as you might want to call it that, how can you actually show that the El Nino phenomenon is autonomous from the rest?
Now,
I mean,
what we found that during time of El Nino, the links that come into this regime, this is the El Nino basin regime, they become weaker. The similarity during time of El Nino, we take 1 year for example, or several months during El Nino, and we see that the links become weaker. The similarity between climate here and here becomes weaker even before El Nino. And this is, and later they become more. And the links outside, from year to year, do not change. Because you can have a direction of the link. I mean, I didn't explain that. The link has a direction. You can make cross correlation. You can see if this one is this one, or this one is, which one comes earlier. You see, because the cross correlation, the peak is not in the center. It can be 1 day or 2 days or 3 days later or earlier. So according to this, we find the direction. And we saw that the direction of the links during El Nino mostly from here to outside, but not inside. That's
but the direct measure of autonomy or not is then, let's say, simple cross correlation, so there's no additional functional layer or something.
Not in this. I mean, what we have is only we see evidence that there is some weakening of the links going inside El Nino during the El Nino. That's what I think.
Any other comment or question? If not, let's thank Professor Havlin. All of you are invited to some refreshment here. Probably will take a couple of minutes to be ready, but it's arriving, so you can go. But for the people going to the link network excursion, don't be too involved with the refreshment, because at 4 we have a bus. Okay, at 4 we have a bus leaving from the parking, which is just going up the stairs to the left. So to the parking. Okay, the rest is the refreshment should be in the red. Thank you very much. No, I mean, questa per later.
I know. The technical arrangements. Yeah. 5 minutes. Here with this.
It was okay.
It was very warm. Because it's a feeling, then they can go
we need to pay for the accommodation. Take care where the end of this.
Here outside.
I think
Victoria, it's in front of your headquarters.
you have a credit card or something, I would say, or you have a, is it possible for you to pay? Because you will get it back, you will get money back.
I see.
When you pay and get paid.
Okay, I see.
You will, big check is maybe you will wait for it.
I see.
You will get paid it.
I see.
But you can get money before.
How
much you pay?
I got sold 5,000 shekels.